Am I audible on Zoom?
Yes.
Okay. Yeah, sounds good. So, hi everyone. Welcome to my talk. Today I'm going to present my works on learning camera view selection in instructional videos. So, what are instructional videos? These are basically videos that are made in order to teach somebody how to effectively do a skilled activity. So, the internet is full of such videos, from videos on how to pack a suitcase like Marie Kondo to videos on what to do after you attend the call of nature. So how does a typical instructional video look like? It looks something like this. So yeah, as you may have noticed, the camera viewpoint in an instructional video switches depending on what stage the activity is at. Sometimes the camera view shows a close-up of the activity, and sometimes it shows a wide angle view. But how do you make such a varying view video? The standard way to do it is to either do a post-capture editing of a multi-view video or perform active camera control when shooting the video. However, both these processes require manual effort, and as a result, they are laborious and time consuming. This naturally raises the question how to automatically select the most informative view sequence for making such a video. To answer this question, we tackle the task of view selection in multi-view instructional videos. In this task, given the video of an instructional activity captured using multiple cameras, the goal is to select the best camera view at each point in the video, such that the chosen views illustrate the ongoing activity most clearly at all times. Before proceeding any further, for those of you who are not familiar with the concept of narrations in instructional videos, I would like to quickly explain that because I'll be using the concept quite frequently in the rest of the talk. So narrations are basically dense captions found with instructional videos, which are independent of the different camera viewpoints, and they provide a holistic description of the instructional activity. So for a controlled multi-view capture setting, a human annotator is asked to watch all views of the video and note down a detailed caption of the activity, and this becomes the narration for the setup. And for an in the wild capture, narrations are usually the demonstrator speech transcribed to text. In this task, I will specifically focus on how to tackle view selection in instructional settings that have a limited number of best view labels. Since, as I just discussed, collecting best view labels at scale, which involves watching all views of a video clip and annotating the most informative view, is expensive and time consuming. To this end, I'll introduce two complementary models for performing weekly supervised view selection. Our first model is called LangView. In this method, we use the view agnostic activity caption, or in other words, narrations, to provide weak supervision during our view selector training. Our second method is called switcher view. In this model, the key idea is to infer human view choice patterns from unlabeled but edited in the wild how-to videos, like videos on YouTube, which are available at a very large scale on the internet. All right, let's now dive into the details of the first method, which is LangView. In this work, we tackle a view selection task where, given a multi-view instructional video, the goal is to choose the best view in the complete absence of best view labels. Here, the key idea is to use text descriptions of the video to provide weak supervision to bootstrap the view selector training. Specifically, given a multi-view video, we feed each view to an off-the-shelf video captioning model, which produces a view-dependent caption for each view. Next, we compare each view-dependent caption to the view-agnostic ground truth caption of the video to compute a quality score for each view. Finally, we choose the view with the highest quality score from above as the best view pseudo label for this particular instance and use it to train the view selector. Here we show our view selector at work on the EgoExo 4D dataset. On the left, you will see all views for the video. In the center, you will see our model's chosen view. So note here how our model chooses the ego view when showing important grips. On the other hand, it picks an exo view when the climber moves on the ground, looks away from their hands and feet, or falls down. Here is a similar example from our second dataset lemma. So here you can note like how the model chooses the ego view when the person is looking at their hands when interacting with objects. For example, when the person was initially taking the cup from the shelf or was pouring the milk. On the other hand, it picks an exo view when the person is moving across the kitchen or when they're not looking at the objects involved in the activity. For example, when the person in the middle of the video was closing the fridge but their head was turned away. So here are some quantitative results from an automatic evaluation setup of the LangView model. So for automatic evaluation, we judge the view quality by computing the quality of captions and action and object concepts as predicted from the chosen views. We compare against a bunch of different baselines. The first set of baselines are naive heuristics like predict ego or exo at all times, or randomly pick a view. Our next set of baselines tries to pick a view that maximizes the visibility of interactions between the demonstrator's hands and objects or maximizes the visibility of the body. The next baseline is a state-of-the-art view selection model. And the final baseline is an alternative but naive way of using language. For this baseline, we pick the view that produces the longest caption as the best view. This assumes that the longest caption carries the most amount of information about the activity. Our model outperforms all baselines on both datasets across all metrics, showing the benefits of our language-guided training. Please check out our paper for more details, including human evaluation of the models. All right, let's now dive into the details of our second method, switcher view. At a high level, this method relaxes the assumption of access to multi-view videos and instead uses edited single-view videos for learning view selection. In LangView, we learn view selection in the absence of best view labels. In contrast, in this work, our goal is to learn view selection with limited labels. To do so, we learn human view choices from unlabeled but edited varying view instructional videos, which are found at scale on the internet, by solving a weakly supervised view switch detection task. Specifically, given a varying view instructional video, we learn a model that given any time t in the video, uses the past frames and past narrations and the future narration to predict if the view should stay the same at time t+1 or if it should switch. Next, we take this model and fine-tune it on multi-view data with limited labels for performing view selection. Note that in this work, we are interested in capturing view transitions between two broad categories of views, ego and exo, since deciding whether to take an ego-like close-up shot or an exo-like wide-angle shot when capturing instructional activities is an important problem by itself. We leave tackling more fine-grained view selection to future work. To solve this view switch detection task, we design a model that is composed of a view pseudo-labeler and a view switch detector. The pseudo-labeler predicts the primary viewpoint of a video, that is ego-like or exo-like. To do so, given a long video, it first segments it into shots where a new shot begins when the scene changes according to an off-the-shelf scene detector. Next, it segments each shot into fixed length clips, predicts the view type for each clip, and finds the view that is dominant across all clips in the shot, and finally sets the pseudo label for each frame in the shot to this dominant view. Doing this short level aggregation of the view type pseudo labels reduces pseudo labeling noise, especially at the short boundaries, and improves model performance. For doing view switch detection, we treat it as a classification problem, where the goal is to classify the desired next view given the past frames, narrations and views, and the next narration. In our setup, since we assume that the past view is known, it's enough to predict the next view to determine if the view should switch or not. Our view switch detector begins by encoding the past frames using a frame encoder and past narrations using a large language model encoder. It then augments the narration features with temporal information by computing the mean of the start and end times of each narration relative to that of the first past narration and encoding it with a temporal encoder. Further, to make the frame and narration features view aware, it embeds the past views using a view encoder and adds the view features to both the frame and narration features. Next, it takes a bird style CLS token and encodes it with a CLS token encoder. It then aggregates all these features using a transformer-based feature aggregator. Finally, it takes the transformer output that corresponds to the CLS token and passes it through a classification head to get an estimate of the next view type. We train this model using a cross entropy loss between the predicted next view and the next view pseudo label from our pseudo labeler. To use this model for view selection, we just use the frame encoder to also encode the frames from all future views and pass these encoded features to the feature aggregator in addition to the other features that are already there for the view switch detector. And finally, we fine tune a pre-trained detector on a small set of best view labels for the task of view selection. For more details, please check out our paper. Here are our view switch detection results with the how to 100 million dataset. For view switch detection, we compare against multiple methods, including heuristics like PredictEgo or EXO for all examples, randomly choose a view, or choose the view on the basis of pronouns detected in the future narration. And we also compare against retrieval baselines that output the view pseudo label for a retrieved training sample, where the retrieval is done using the past frames, past narrations, or future narrations. Here are our results for view selection on EgoExo 4D. In addition to heuristics and retrieval baselines, we also compare against our previously discussed LangView method. Our model outperforms all baselines on both view switch detection and view selection on both datasets. We also test the impact of the training best view label count on our model's view selection performance. We notice that the lower the label count is, the higher is our improvement over the state-of-the-art LangView method, showing that our method is robust to extremely label scarce settings. Here we show a qualitative example from view switch detection. We show its past frames and narrations on the left and the next frames and narrations on the right. Note that the next frames are unseen. In this instance, note how our model likely relies on the next narration to choose the view, since mentioning the chicken cut type probably indicates a close-up is required to be able to better see the cut. Here we show a successful view selection example. On the left, we show the past frames and past narrations. On the right, we show the next frames from the candidate views and the next narrations. Note how our model bases its predictions on the past narrations, where the show of displeasure by the camera wearer can indicate a switch to ego is better to show the issue. It also probably uses the next narration in the same example, as mentioning minute details like how good the door looks probably means a switch from exo to ego is required. This brings us to the end of my talk. Before taking any questions, I would just like to say that I'm presenting the switcher view paper in the morning poster session on Wednesday. Feel free to drop by. Thank you.
We have time for one question. I have one for the first one.
Yeah.
So how well does that quantitative evaluation align with the sort of human preferences when you did that study?
Yeah, that's a good question. So we saw that even when we did the human evaluation, though, our method was beating the baselines. And another reason for this kind of a correlation is that in our case, the goal is very objective, compared to, let's say, video editing in, for example, movies and other kinds of scenarios where you kind of rely more on aesthetics, so it's more subjective. But in our case, it's kind of catered towards being able to see the activity as well as possible, so there's more objectivity. So that way, there's a better alignment, and yeah, we saw that even with the human studies, we could see similar differences and so on.